Welcome to the talk, Spectral Audio Modeling. Why did it evolve and do we need it now? ADC23. So what I want to do with this talk is give a zoomed out overview of spectral audio modeling from evolution to AI. That's way more than I can do in this talk, but I will try to hit some highlights and hopefully convey some insights that are useful. So my intended audience is people like me, the audio signal processing engineers who are trying to keep up with the AI audio stuff going on. So I've been reading and I want to share some of my, wrap up on that. And then hopefully it'll also be useful for people doing AI audio and who do not have a signal processing background, or at least not spectral modeling all the way through the way I've lived it over 40-something years. And so some relevant questions are, why did we evolve spectrum analyzers in our ears in the first place? Why do we walk around with hardware spectrum analyzers transforming vibrations into a spectrogram on our neural inputs to our brain? And how did that drive our use of spectrum analysis and processing? How did AI pick up on that, and will it even continue to use spectrum since it can learn it if it wants or just forget about it if it doesn't? So we'll start with human hearing, why spectra, spectral synthesis, AI audio synthesis, spectra and AI. And over here is the outline more or less by chapter. And so you can download these overheads from the website for ADC23, but you can also get it on my homepage if that's a more convenient search at some point. That's where I would go to quickly download something. And the main reason to download it is that there are many more sound examples than I'll have time to play, because this talk, I used up to DDSP, I use it as sort of the first lecture in my Music 421 class that I give at CCRMA. So here's the current building, the Knoll, but we started out in the Stanford AI lab, and John Chowning was the founding director, and I started there as a volunteer from the Valley, and his first task for me was to build a 3D rotatable spectrogram that he could run on the III vector displays at the AI lab. Max Matthews, the father of computer music, retired at CCRMA and was around a lot. And because I knew him, I wound up getting an internship at Bell Labs working with the premier signal processing people. I was working directly for John Talon, but going to the same meetings as Larry Rabiner and Jim Flanagan, Bishnu et al., and so on and so forth. It was an amazing place to be. And so I got my grounding there. I also got my grounding in the software at CCRMA by Andy Moorer, who was importing latest results into our software base there. So I've been doing it ever since, because I started teaching it there. So I ended up being the person teaching signal processing. So I have a beginning course in spectrum analysis and a more advanced course where I try to import the latest results from the conferences, ICMC originally, and nowadays it would be DAFX and other conferences. So that's just what's been going on for all these years. And so this is sort of my intro to that and some highlights. But it really nicely segues into AI, because DDSP, differentiable DSP, picked up on science plus noise, which is, right at the end of this story here. And it's just the sort of next big jump in additive synthesis practice. And then we get into the more modern stuff. Well, I say more modern, like a few years later, we have generative AI audio based on these new audio codecs. I would say they're based on SoundStream. And the idea there is to go from a continuous waveform to a vector, a sequence of vectors, so that you can use the large language models, put it through a transformer, align it to text and all that stuff. So I want to look at a little bit of that and just sort of, zoom out. But, because there's such a large scope, I can only hit the high points. But the overheads will give you more. You'll be able to drill down, hear more sound examples, get more links. And so, and these courses are links as well. So you can click on this to get to the 4 textbooks that are free online, and all the source materials, all the course materials are there. And so, I've been talking about spectral processing, but I also have another half on physical. So, for your sources, your models are a good choice for your musical instrument sound sources, because you want them to be sensitive and expressive and, tuned in to the performer. and understandable. And in terms of AI, you would say you have structural priors given by the musical instruments that you want. Now, this is a very traditional approach, but you can expand from there, and you can build it other ways. But that's the basic layout here. So we've got our sources in the physical filters and models, and then we have spectra, and then we evaluate our models in terms of what we hear and so on. And so there's a much bigger story here. Don't let me oversimplify it, but this is the general theme of what I've been teaching for all these years, and why I'm trying to update it with AI stuff, and why I'm trying to blend them in ways that I'll describe. So early spectral audio signal processing. Well, I guess it started in the ocean with the hardware that was evolved for hearing. A lot of interesting gadgets were evolved to improve sensitivity to sound and frequency response. Even today, our neurons start rolling off at around 1 kilohertz, 1 millisecond firing rate. And so to get up to 20 kilohertz bandwidth in the ear, we really need to do something. And so what we evolved is this spectrum analyzer here. So the sound comes in, gets spatially filtered for elevation perception and such. And then you have your eardrum, your hammer, anvil, and stirrup impedance matching bones to get in from air into liquid. And then we're generating a traveling wave down the basilar membrane. And the lower the frequency, the farther it goes in. And at some point it resonates, so the particular frequency might resonate here, and then this nerve will pick up that vibration, and off it goes in the auditory nerve. And this is our balance system. So this is a depiction of the basilar membrane. 20 kilohertz is at the entrance. A lot of us have that all worn out by now, and then as it goes in, the frequency resonance is lower as it gets, less stiff and more compliant. So this is a depiction of the resonances as they get some distance down the basilar membrane, resonate, and get felt by the hair cells. So this just to sort of set the stage as to why we're doing spectral anything. It's because we all hear through a spectrum analyzer. So it's really driven a lot of the architectures of both sound perception and sound production, such as in the water organ, the hydraulis. So the polyphonic keyboards will generate an additive synthesis of different timbres, in this case pipes. And so that goes back to the 3rd century BC. And if you're satisfied with one voice, you can go back 60,000 years and find Neanderthal bone flutes, and you can also find them made of bone and ivory, which is obviously something that was valued. And so this was, you could say it's a direct result of the way we hear. So telharmonium is another interesting signpost along the way. This was inspired by the telephone. And so it was a vision of creating centrally music that would go out over the telephone wires. So this is the controller keyboard. And on the other side of this wall, you have what looks like a factory full of rheotomes that are rotating. Here they are in the patent. And so here is someone standing next to a rheotome. So you can see it's kind of a rounded square wave synthesis kind of system. And this was said to have influenced the Hammond organ tone wheels. So the Hammond organ tone wheels were much, much smaller, but apparently there was a connection there. So that was, around the turn of the 20th century. And then we get into the 1920s. Then we start working on the vocoder. And then the voder was used in the 1939 World Fair to demonstrate the synthesis technology of the vocoder. And here it is. It's a performable speech synthesizer. So you're playing the formants. So now you're actually manipulating directly the spectral envelope of the speech, the formants, the formant resonances. And here's a wrist bar for switching between voiced and unvoiced. And then there's a foot pedal down here for pitch. And you can make it talk. And so here's a diagram. Here's another diagram. I'm going to speed through these because we just don't have time. These are 2 YouTube videos that I recommend. You can hear them, and it's really an incredible thing in 1939. But meanwhile, back in the vocoder space, Manfred Schroeder told me that he was working on this in the early 1920s, but the official date is 1928. we had a synthesis system very much like the voter, but we have an automatic analysis. So instead of just manually coming up with the controls, we would measure them, measure 10 band powers through time, and those would be the gains for the bands on the synthesizer side. And you have to detect whether it's voiced or unvoiced, and you have to measure the fundamental frequency. So that's about it. So you have this nice parametric model for speech, and this could be thought of as an early source filter model for speech, and we still do those. Linear predictive coding is one. This is probably the biggest one. It's still used in certain speech compression standards. And you can say it's architecturally similar to WaveNet. So in the AI world, WaveNet is a nonlinear autoregressive predictor for samples of sound. And this is just a linear autoregressive predictor for samples of sound. So there's not a whole lot of similarity in the results because, one's a nonlinear neural net and this is a linear prediction. But the architecture is the same in that sense, the autoregressive sample prediction. So here's a diagram of the vocoder filter bank, and that's the analysis, and then you can compress it and transmit it. Get many more phone conversations on the wires. This was Homer Dudley's vision, probably a factor of 100 easily, and reconstruct on the receiver side. So I've got some good sound examples here from some nice software for the vocoder that we've been using, and there are a lot of classic effects here. You can hear them. You'll recognize them if you want to listen to all that. So we were using the phase vocoder. So I sort of glossed over the phase vocoder. That's the vocoder plus phase. So in '66, Flanagan and Golden added the phase estimation measurement to the band measurements, and a little bit later it was done by the FFT. So the short time Fourier transform became the basis of the vocoder, the phase vocoder. And so with phase, you can now reconstruct very accurately. So it could be an identity system. If you don't modify the band gains, you can really just reproduce the waveform to within numerical precision. So that was the basis for additive synthesis. We would analyze with the vocoder and synthesize with oscillators. And this looks like one of Max Matthews' oscillators in computer music from Music 5 or something like that. So you have your amplitude envelope, you have your frequency envelope, and these were measured by isolating individual overtones in a band. And so this is very, very big part of computer-generated sound, I would say, in terms of the total history. So here's an example of an amplitude envelope, frequency envelope, measured in the bands of the vocoder. And so this kept going. Now, meanwhile, back in 1975, John Gray was a psychoacoustics PhD student, one of the four founders of CCRMA, who was doing analysis of timbre for, his approach was to extend steady state timbre to time varying timbre. So the classic psychoacoustic understanding of timbre was based on steady state tones. He wanted to go to the time varying case. And so the computer music project was a perfect place to generate stimuli for his experiments. And this was before we were using the FFT or anything like this. Was the heterodyne comb. That was by Andy Moore. But it's equivalent to an FIR filter bank like the FFT implements. And they were also aware that you could greatly simplify this. So I'm sure Homer Dudley would be very happy to see that you could reduce the envelopes by a factor of 100 or so, a couple of order of magnitude, and get really good quality reconstruction. And so there's a diagram of the additive synthesis. And here is sound examples. And so you can play these if you want to hear the individual toots. And so FM was another spectral modeling approach. Not everybody thinks of it that way, but it was certainly voiced that way, according to what I witnessed. So John Chowning started that and developed it and wrote it up for the Audio Engineering Society, got Yamaha interested. That led to the DX7 synthesizer, which is actually being voiced using AI nowadays. I've seen some projects. It led to the OPL chipset, Sound Blaster cards, and all Sound Blaster compatible cards. We were getting these things. It went on to be used in cell tones for much longer. And so, meanwhile, physical modeling was just getting going as well. So there's the FM formula. You have your modulating oscillator amplitude envelope. The amplitude of the modulator sets your FM index. There's your carrier frequency and amplitude, and out it goes. That's all there is to it. It's a very simple thing. So you can think of it as a compression format for additive synthesis. So if you're doing additive synthesis and you want to reduce the footprint of it, you can think of FM as a way of doing that, getting a much smaller footprint. And so here's an oscillator pair that will generate a basic brass tone by making the modulator amplitude proportional to bandwidth. So by making proportional to amplitude, then bandwidth becomes proportional to amplitude, and you get that kind of brass effect from that. It's a very, very simple but effective FM patch. And here's a plot of the Bessel functions describing the harmonic amplitude. So if the FM index is 0, here's the FM index, take that down to 0, you just get the carrier. That's, I guess that's, I would say harmonic 1, but maybe it's 0 in this plot. And then as you increase the FM index, then you can see the other harmonics start to come in. And most people work with it down in this range. When you get up here, you get that sort of classic nasally FM sound. You recognize it as FM. Down here, you're not as likely to recognize it that it is FM. And so, and this is very, you'll see when I show you the voice example why that's so effective. So, so these are examples, and let me go ahead and play one. Let's play the bass because I want to show you how the voice works. So now we have this kind of approach for synthesizing any kind of voice. You have formants, and so here's 3 formants, 3 resonances in the spectrum of the voice. And so what you do is you just select one of the carrier oscillator frequencies to the harmonic nearest the first peak frequency, and then the second carrier goes nearest the second, and so on. And then all of the modulation frequencies are set to the fundamental. And so that means then that the first carrier will expand into sidebands and give you that formant group, that, the harmonics under that resonance, and so on for the second and third. So this is how you basically put together a spectrum. So you think of, the oscillator pairs as generating clumps. They can generate little formant groups, and you can piece together very general harmonic spectra this way. And of course, they can be inharmonic. You can pull these apart. The only thing that has to be the case is that your sidebands have to be uniformly spaced with respect to a particular group, because that's a constraint of the structure. But you can stretch the tuning of the groups. Okay, so that's FM, and now we go to sinusoidal modeling, which was a big topic. It evolved quite a bit. So we were having a little trouble with the vocoder because it's a uniform filter bank, and analyzing piano was inconvenient because the partial overtones are stretched. So we needed to either stretch the filter banks, and we did do that. We were able to put together peaks from the cracks between 2 vocoder channels. But wouldn't it be nice to just follow the peak wherever it goes? And that's what we did. That was the partial program. And so this was happening before as well in other fields. And so you get a track of frequencies through time, and you just have to associate them. So you want to use a small hop size so you don't lose track of which track you're in, that sort of thing. And then a little bit later, we noticed that the sinusoids are really great for tonal components, but for noise components, you just needed too many of them. You needed many, many oscillators to get a good noise sounding signal. And so that's when we added filtered noise as a modeling component, a spectral modeling component. And so Xavier Serra was the PhD student who really pushed this out the door and made it made all these great demos. These are his original thesis demos, and this was really a nice big jump forward. And so here are some effects: pitch shifting and voice effects. And here's one that I'll pick out. This is a cross synthesis where you take the spectral envelope of a voice and impress it upon a flattened spectral envelope of the creaking mast of a ship. We were away a while ago. So these examples are all here. Another thing we did was transient modeling. So you have sinusoids for the tonal components. You have filtered noise for the stochastic components, things like breath noise in a flute. But what about transients? Now, neither of those models were really good for transients. Now, what MPEG does is it switches to a short window, and we can do that. But a more accurate thing is to just keep the initial attack unchanged. Just hang on to that chunk of waveform, and then segue to a phase-matched sinusoidal expansion. So you use the original attack, let's say 1 period's worth, and then when the additive synthesis begins, the initial phases had to be correct so that they get a nice continuous waveform at the crossover point. And we found that we didn't even have to crossfade. You could just go right into it. Of course, you're also in an attack where you're not going to be hearing an isolated bump like you would in a tonal component. Anyway, these are here as examples as well. So then the next big step forward was multi-resolution spectrum analysis, and that was Scott Levine in his dissertation. And so he did a science plus noise plus transient system, but the big step forward was the multi-resolution spectrum analysis. And that's interestingly something that was discovered in AI audio as well, that you really want multi-resolution spectrum analysis for the loss functions and and the adversarial and reconstruction losses. So it's a really important principle for audio, that the spectrum is multi-resolution in our ears, and so our analysis needs to reflect that for best results. And so what that really gave us was the ability to model ensembles. Before this, all of the examples before this time that were put out publicly were one voice at a time. And that's interestingly the same for DDSP. DDSP does not try to model ensembles. It's just one voice at a time. Part of the reason is that the pitch detection is one pitch. It's a pitch follower for one pitch. So that means you can do general coding of audio. And so here are the pieces of it. And those are sound examples you can listen to. Now for timescale modification, you have your science plus noise component just in terms of envelopes. So you can stretch them and squeeze them to as much as you need. They're just envelopes. But the transients, those are, faithful, and you just want to move them through time. You don't want to stretch them. If you do, you'll get artifacts, right? If you stretch out a transient, then you'll get an inverse squeeze to the spectrum. You get this change in formants and so on. But the envelopes, or time domain envelopes, they can be stretched quite a bit. Now, it does change the relative phase across the harmonics, and that can be heard as reverberation and so on, but it's a very robust thing to do. Let me give you an example of that. Here's the map of the time frequency plane with the multi-resolution spectrum analysis, and this is an attack that is being uniformly modeled, quantized really. Here they are in window form. So here there's the lowest octave, how the windows overlap, and then the next octave up, they get shorter and they're overlapping 50%, and then the next octave up. And then this is the how the windows look going through a transient, which is right here. And here's how the time frequency map looks in a sort of wavelet sort of approach, where the transient is gated not rectilinearly like this, but sort of in a band appropriate way. So the low frequency band is longer. I did not want to go to this level of detail because I'm going to run out of time. I'm trying to hit the highlights here. This is the bark band noise. And, I've got a link to his thesis right here. So if you want to read all about it, you can. And there's papers as well, of course. So I'm just trying to hit the high points here. What I want you to notice is that we're just doing more science plus noise plus transients. We're doing sinusoidal modeling. We're doing spectral modeling of audio. And what we get for that is all sorts of malleability in the representation. So let me show you just one example. Timescale modification. So here at 1, there's no modification, but here we're going to stretch it out by factor of 2, and here we'll squeeze it by factor of 2, and let's listen to what this sounds like. I wanna rock right now. 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 So the trick is, changing the time scale while not changing pitch. And so the dual of that is to change the pitch without changing the time, and it works great as well. Okay, finally we make it to the AI world, and about halfway through, that's good. So differentiable DSP was a big step forward. That's when we used neural nets to compute the amplitude envelopes and the filter noise envelopes. And so it's a science plus noise model. And so you have your audio and you get F0, the pitch, from the CRAPE pitch detector. That was from NYU. And then you estimate loudness with some kind of RMS level or whatever. And this is assumed to be one voice. And then what's left after you take out pitch and loudness? Timbre. So the Z vector is nothing but a timbre vector, right? So then you can decode it and get envelopes and make audio. And then the loss function does involve multi-scale spectrograms. So this is good audio practice. So there's the encoder, starts with MFCC. That's a very standard thing in speech. Mel frequency capsule coefficients and gated recurrent unit. This was right before the transformer hit, and so this might get replaced by a transformer later on. But a lot of people still use gated recurrent units instead of transformers. I can refer you to TonicNet as an example of something that works as well as Music Transformer with a factor of 10 less, order of magnitude less processing, comparable results, order of magnitude less processing by replacing the transformer with a gated recurrent unit. Anyway, so that's the general idea there. And then here's your decoder. I find it interesting that the pitch and the loudness are not just preserved. You don't just feed them across. You give them their own multi-layer perceptrons so they can be mapped freely for things like style transformers. There are a lot of transformations that are supported by this system. And so out it comes. And now you just have a whole new level. And these are really good examples. And I do have a link here. Of course, you can just search for this, GDSP, Google Magenta, but this link will take you right there. And you can hear the sound examples and study it. It's really well done. And the code is really nicely documented. Just a really big shot in the arm for all of us. And got us all going in this area. Okay, now let's kind of fast forward a little bit to what's going on now. As far as I know, the state-of-the-art music generation is Music Gen, and that came out this year. And it follows on the heels of Music LM, which just came out earlier this year, and then Audio LM is similar. And so these are all in a family of systems that will generate music from text, so you can talk to it and say what you want. And the reason it can do that is because it encodes the audio into a sequence of vectors that can be aligned as a latent space to text. And so you can then have interactions. They call it multimodal. I'm sure you've heard about it. So the actual coder, though, is you can think of it as just an AI audio codec that's somewhat general. So I don't have any language model stuff here, but this vector sequence can be given to a language model kind of thing, a transformer or whatever. But just the coder part, you take the waveform and you go through this sort of CNN style thing. It's actually WaveNet style. Let me go back a little bit and talk about the history a little bit. So WaveNet was another really big sea change in audio synthesis. This was a text-to-speech system that worked extremely well. Everyone was surprised how well it worked. I'm pretty sure, and it was very influential. And so here's some other highlights. I will say, go to the DataBots page and listen to these. There's radio stations that are running all the time on YouTube, and you can hear them, and they're really quite good. And so other highlights here, this review paper is a nice wrap up to that time. But now we're talking about this sort of latest music generation system, which all use AI codecs, audio codecs, very much like this. This is the SoundStream codec in particular, and there's others that there's encodec, and there's Descript. Here they are written out, so you can follow this. But they're all based on SoundStream, really, which is, I believe, the first big use of vector quantization, in particularly residual vector quantization in the heart of it. So let's notice that the discriminator is sort of a GAN style thing where you have this adversarial loss as well as reconstruction loss. Let's come back to that. So WaveNet has this sort of architecture. So you can think of this as a nonlinear predictor of this sample of sound. And so during training, you're just predicting the next sample of your training sample. And then on synthesis, you're just predicting the next sample from the previous samples that you've already generated. And this is the style of dilated convolution that's used. And it's just been enormously successful. And you could say that, we're still using that. That's what these convolution, the encoder convolution essentially indicates something very similar to that. And here's something that really caught my attention. So in the WaveNet paper, it said, traditionally, speech recognition research has largely focused on using log MEL filter bank energies or MEL frequency Spectral coefficients, MFCCs, but has been moving to raw audio recently. And so when that came out, people were saying, well, we're done with features. The whole field of music information retrieval is obsolete. If the neural net wants a feature, it will learn it. It will evolve it. Let the weights decide. So it looked like signal processing was just being optimized away in favor of a black box neural net. And it was, but it's also very expensive. And so I want to show you some successes of signal processing to come back into the picture. And so here we are at the latest that I know of, the best high fidelity audio codec that's used in these sorts of systems. And so it's based on SoundStream followed by encodec. And so this is actually the figure from encodec, one before Descript, but it's pretty much applicable. It's close. So here are your one-dimensional convolutions. I don't believe Descript has this LSTM in here. And then it goes into the residual vector quantizer. You have to learn a code book here. There's actually loss functions just for the code book. This is for a projection that's, I don't think, used anymore. And so it's pretty complicated learning these code books. But it's vector quantization in a learned code book. And then you have your decoder here, called these transposed convolutions and 1D convolutions. And so here is your discriminator, and here are your reconstruction losses. You have one for the time domain, you have one for the frequency domain, so you get spectrograms. And so this is where signal processing survives, is in the loss functions. And both the reconstruction and the adversarial loss, because you see this is a real and imaginary part. It's a phase-sensitive spectral loss, and it's multi-scale. You can see that it's explicitly multi-scale. And so the systems have learned that they want to be multi-resolution in time and in frequency, and so you're seeing that now. And in fact, that's part of what's going on with this convolutional dilated convolutions, is that on the first layer, you're sort of looking for very short features, very short time series. And then when you go to the next level, you're dilated and looking for larger level things. So you can think of this as sort of downsampling as it progresses through. And so it's operating very much like a CNN, convolutional neural network for images, where you're looking for fine-grained features and you progress up the layers and look for larger scale features. And that finally gets you to a good embedding space where you've got a nice feature layout for your vectors, and then you encode those. You allocate codebook entries to that, and then the decode has to invert all that. It's kind of an upsampling process, you could say. And so that's the sort of state of the art now in these AI codecs. But one really key point is that they are very, very much driven by spectral audio signal processing. In other words, we've got a strictly enforced model of hearing. So let's say the early stage of hearing here, the cochlear modeling stage, some kind of auditory spectrogram going on here. And it's multi-resolution the way based on our membrane works. So that really is important. Loss functions really matter for driving this thing. But as far as the actual coder is concerned, it's basically time domain. My name for it is neural concatenative synthesis. one of the big things used in text-to-speech systems in practice really is just concatenative synthesis, where you just have phonemes in a big database and you just string them together. And so you have ways to segue from one phoneme to another and have it at any pitch. You get an independent pitch contour. So it's just kind of having to invent that. It's having to invent what goes in the database, and then it has to be able to string them together. So in the database, you need an index not only for every little phoneme, but also for every phase that it might need to come out at, right? So these things have to string together in phase. It's got a lot of waste in there because it's working in the time domain, but it's working really well, and it's getting the best results. It's getting the best compression. For low bitrate speech, it is clearly out front. I would not say it's out front for high fidelity audio, just because it's not as good as MPEG. I mean, MPEG AAC is just significantly better. It is high fidelity relative to everything that came before, and it's very, very good, and it's great for casual listening. It is not high fidelity in the sense that we would, want to buy our CDs in this format. So this is summarizing what I just said. Okay, so now let me just tell you some more ways that spectral methods are coming back. SoundStream. Already, the SoundStream series, let's say, show a progression from end-to-end learning in wavelet in the WaveNet to the use of multi-resolution spectral reconstruction and adversarial losses. And by the way, reconstruction loss means you're just trying to match the spectrogram. So this should be like comparing your original data spectrogram to your reconstructed spectrogram, where the spectrogram is an auditory spectrogram, where it's what you see is what you hear. And then adversarial losses tend to be a little bit more strict about how natural they must be. In other words, they're looking for things to be in distribution. And that means that if you have some very strange sound that's not at all typical, it will have a hard time getting through the detector. It'll be declared fake, right? So your adversarial losses are a little bit tricky. And the one thing I would do with those is to give them a sort of audio filtering, a sort of a perceptual audio filtering, so that there's no way it will use, you don't want it to try to use inaudible cues such as, masked information to declare something out of distribution and unnatural and therefore fake. So you have to be careful with these. So in principle, we could learn these loss functions, right? And again, you're supposed to learn your discriminator. Well, that's a lot more work. And so my take is that what's happening is that traditional signal processing is making a comeback to save training effort, to train data, to save data requirements, because you're going to get there in the end, or you want it to get there in the end. You want it to have an auditory front end built in there somewhere. So just give it that. And so it saves a lot of work. Now here's some examples where the spectra are pushing back into the decoder, the formerly pure time domain CNN style decoder with a quantizer in the middle. ISTFT-net is replacing the last two upsample blocks of hi-fi GAN with an ISTFT, short time Fourier transform. And Vocos, which just came out, replaces the whole decoder by an inverse STFT. So that means then it's forcing the model to be short time Fourier transform coefficient. So we're back to spectral modeling all the way. And what's really, really exciting to me is that it matches state-of-the-art performance using an order of magnitude less computing. So this is good stuff. We love seeing this. Those of us who want to, keep our toolbox. Here's another place where spectrograms are winning and where they're really required. This is Josh McDermott's lab at MIT, one of the recent papers. This is a neural net, and they start with a cochleogram. So it's like a spectrogram plus the nonlinear filtering of the ear and so on. So you can think of it as like a deep learning one-on-one CNN style encoding, neural encoding after that. And so they have tasks. So the word classification, genre classification. And since I'm low on time, I'll just let you read this. It's really, really very impressive. I would like to, maybe point out that once again, we could say that the cochleogram should be learned eventually by the neural net, but in principle, you have to simulate, you have to recapitulate evolution from, I don't know, when tetrapods first crawled out onto the ocean, out of the ocean. I don't know, but that's a lot more work. And so we know if we want it to be human, we need this. Another thing I want to mention is that this thing performs at human level with similar errors. And if you want those similar errors, you need this. So they did try getting rid of the spectrogram front end, and they found that the predictions were no longer human. The way that the feature maps evolved after that became very alien to us. Here's another one I like. This is a project by Pratik Verma and Ron Schaefer, as in Oppenheim and Schaefer. And it's just a 3 hidden layer MLP that is finding the pitch, estimating F0. And so here's the estimate, and the subharmonics get a lot of weight. So what they did was then, they train it up, and then they say, I bet that there's likely an auditory filter bank in the first layer here, or let's see if there is. And so for this neuron, you take the weights leading to that neuron, FFT that, take the magnitude, and then find the peak, and then do that for every neuron here. And of course, there's many more than shown here. And this is what they look like when sorted according to peak frequency. So you can see these are the frequency responses to the weights. And so you can see that you get a lot of weights in the range of F0s in the data set, and then it becomes more, typical auditory filter bank beyond that. So it's just showing you how the weights are spontaneously forming, an approximate auditory filter bank that has been adapted to the task. It's adapted to the data, and it's adapted to the task. So I think what this suggests is, why don't we just give it a differentiable auditory filter bank, and then let it just, move the center frequencies around and maybe the bandwidths, and then it can adapt to task and adapt to the data, and save itself a lot of work. It doesn't have to. These are non-parametric weights. I mean, every sample here can be anything. And so, there's a lot of training effort to get those weights to become what looks like, a windowed sinusoid. So, if you know what it needs, give it to that and make it differentiable, and you should be able to train it up faster. This is my hypothesis. We didn't do this. I'm just, I'm giving my reaction. This is my, reaction to things. All right, so just to summarize, we see all these benefits, and this is what I just talked about, except I did not talk about diffusion at all. And I just want to mention that a spectrogram makes a lot more sense as a target for reverse diffusion than samples, right? So we're using spectrograms there, and you can also use a MIDI piano roll, or even just a visual score, a written score. So refusion is won by stable diffusion, and that's a good example of how this is working. So the techniques in Midjourney and DALL-E and all that are at play here. And so the sing-song system is also interesting. You give it a melody and it generates accompaniment. They're trying to give you controls that are sort of MIR-based, feature-based controls that we know and love. Another one is anticipatory music transformer that allows you to essentially work in a music workstation and do in-painting of your score, that kind of thing, your DAW representations. So my feeling is that we like end-to-end systems for showing us how well we should be able to do, but then let's come back and embed known signal processing structure that we know that it's evolving the hard way, and make it differentiable ideally. And then if you make the system small, then it's more clear, you're more likely to find what it's doing, like that, auditory filter bank in the F0 task. So this is what I've been talking up and working on a few things. I have a few projects along these lines, but I don't have anything ready to publish yet. So to just summarize, spectral representations give you structural priors, also called inductive bias, aligned to human hearing. So for example, in synthesis, we can force our synthesis models to the distribution of natural sounds for humans. And we also have error perception tuned to humans. So things like masking are not counted. Human-centered loss functions, minimizing the errors that humans hear most. And this is really done well in things like Descript And so that's why you'll hear just extremely good synthesis at extremely low bit rates. So if you have these structural constraints and sensitivities, then you get reduced model size, training time, data requirements, and computation, which reduces fuel consumption. And that makes it green. It's a good idea. So the thing that really ties it all together is that we do want it to be human. If you don't want it to be human, maybe you don't care. So maybe after the AI apocalypse, we'll be done with Spectra, no baseline membrane in our robots. So here's the summary once again. And I see that I'm out of time, so why don't we move on to questions and discussion and comments.
Okay. Well, thank you very much for this fascinating retrospective. I suggest we would start with a question in the room.
Really enjoyed the talk. I was just wondering, is the state of the art in voice recognition rooted in spectral information? In your opinion?
The state of the art in voice recognition? Well, that you can get a lot of opinions about that. I am not active in the field of voice recognition, but I follow it with interest. So people are. This is really older than ISMIR. Speech recognition has been going on for very, very long, and MSCC is pretty much converged in that context, and we were inherited by the MIR world, and so. To the extent that MSCCs are used, yes, but then there's the LEAF system, which is very recent, LEAF, from Google DeepMind. Check that out. They basically learn a front end. So you can argue, I mean, that question goes to the heart of this talk, what information are we taking out of the signal when we get best results? And the thing is, when it starts out in a neural net, nobody knows, right? But we figure it out. And I gave some examples. But clearly when we do it, we go through the auditory processing. So in that sense, for sure, we do it that way. But if you define the task a bit differently, where human performance is not the goal, then you can get something alien that's very different and better in that task. I don't know if that's a good answer, but those are the issues that.
I think it leads to one more question, which is, with all this, talk about spectral modeling, I'd like to know, in the history, has anyone attempted to look at a physical model of the vocal folds and to pursue the idea from that angle?
Yes, I would refer you to the dissertation of Huiling Liu, Huiling Lu. She had a really nice model of the vocal tract. Very nice and practical. Before that, there was what was called articulatory synthesis, and those were very elaborate physical models. At Bell Labs, they were, Cecil Coker comes to mind, very elaborate models. But Huiling's system was really nice because it was for practical synthesis. It involved the Lillian-Krantz-Vaught model of the glottal waveform, and then also the Klatt model. So Dennis Klatt had a model that was very simple, piecewise polynomial, and then there was a little more sophistication, or let's say more generality, in the Lillian-Krantz-Vaught model. And so she actually employed both of them in a very nice way and got great results. And on her webpage, you'll hear some really good sound examples. And the big thing was aspirated voice. You could get breathy voice as well as the hard-pressed phonation. And that was only one thing. Of course, there are others as well, but those are the ones I know about the most.
Do we have another question in the room? Okay, I think we can go through the online question. The first one is asking if these recent AI techniques can be used with the additive model with sinusoids. They include envelopes for the sound partials so that harmonics can be preserved.
Absolutely. You could build a system of that nature starting with DDSP. You could also try to use Vocos that's more recent. you can impose any constraints you want. It's a very open-ended system. So yeah, I would just start with something close and then just impose the constraints that you want.
Thank you. We have another question. It's, can we rely on audio spectrograms as ground truth, capturing all important aspects of a sound being modeled? Consider, for example, auditory illusions, such as constant spectrum melody, which appears visually as something completely different than what we perceive.
Well, you do have to be careful. What do you mean by a spectrogram? If you're talking about magnitude spectrum over short time frames, then then the question becomes how short are the time frames and how short is short enough. But if you have a complex spectrogram, of course you can do it because that maps one-to-one back to the time domain, and we know that the time domain is sufficient. So if you're not throwing away any information, you're safe, right? But we do want to throw away information. That's where we get our gains. And the ear throws away information. MPEG gets on the order, like about an order of magnitude compression without most people noticing any difference, right? It's because there's so much masked information. So yeah, we're listening to the upper spectral envelope, and there are little details here and there, but on a broad-based level, it's the upper skyline, the upper 10% of the spectrum. So we want to take advantage of that. We can save a lot, and that's why MEL frequency spectrograms are used so much. But you do have to be careful. And there are debates. I've sat through many of them, and it's ongoing.
Okay, thank you. We have another question online. One user saying that it sounds you're proposing to extend the concept of physics-informed to neural networks to psychoacoustic modeling. What do you have to say about that?
Well, I like physics-informed. Well, so psychoacoustic modeling is important for humans. If you want the system to, be human in some sense, to perceive like us, or at least to represent us in some sense. Like for musical instruments, you want the error criteria to be human so that you don't waste a lot of time modeling, let's say, from 20 kilohertz to 100 kilohertz, right? I mean, there's just all this unknown, unheard signal that we don't want to spend a lot of effort on. So that's one reason. And then physical informed structures for musical instruments are important for, basically, you could say constraining you to the manifold spanned by a natural instrument and nowhere else. It's something that the GAN discriminators will like. In other words, it forces you in distribution. You're not able to make a sound that's unnatural for what you're going for. But then that means you know what you're going for. So you have a model and you want something in that space. So physics can give you, useful spaces, useful subspaces of, infinity that behave like we like, that give us instrument families that makes them predictable, makes them understandable and intuitive. And so, yes, absolutely. And so I think the main agenda going forward is combining the state-of-the-art neural net architectures with the state-of-the-art signal processing architectures and blending them in such a way that we preserve state-of-the-art performance, but also maximize, open, transparent structure that we know and understand. And ultimately, it would be nice if all the neurons went away except for maybe some front end that's like a non-parametric weighting function going into very well understood structure. I would like that in my self-driving car as well. I'd like to have absolutely known, understood structure at every stage if I can get it without sacrificing performance. And I'm not giving up yet.
Okay, thank you. I have we have a question in the room.
Sorry if this is a question that you've already answered. It's just that you seem to have quite a broad overview of all of the combinations of machine learning and spectral DSP. I'm really interested in real-time systems and obviously. And I really like the RAVE model that I think came out of ERCAM, and I don't think that they use any spectrograms in their system, and I just wondered if there are any newer models that have managed to use digital signal processing to speed up that process, make things more real-time, low latency. Does that make sense?
Well, before Rave, there was Audio Sculpt, from the IRCOM forum. That's a direct manipulation of the spectrum. My take on Rave, I haven't looked at it in detail, but it is look more like a principal components kind of approach. And you train up a few vectors, you sort of learn a latent space, and then you play back in terms of those. You can, have real-time linear combinations of principal components that have been learned based on data. And so you could guide that in the direction of spectrograms. You could use Vocos, for example, as your sort of starting point. And then you're just playing back a spectral version. You can force the model into a spectral form that way, for example. So yeah, it's wide open. The main thing I think is to just think in terms of transforms. Every stage of a neural net is a transform, and you can just, it's like patterns and patterns and patterns, and the FFT is just one, right? So one layer gives you a DFT matrix, an FFT. And so if you want a spectrum transformation, you can do that in one layer. And so what's really powerful, though, is to stack them up, to do a transformation, make a decision, the neural net decision, basically gate it and prune it and do pattern recognition on it, and then go to the next level on that. So it's like pattern recognition upon pattern recognition upon pattern. I see that as an extremely powerful, well, it's been proven to be an extremely powerful approach. And so you can put ordinary signal processing in lots of places in that scenario. Yeah, the big advantage was very high dimensional nonlinear models that can be optimized by gradient descent reliably. Before this breakthrough, you wouldn't go for a really large system with nonlinear optimization as the way you trained it, because it would get stuck in a false local minimum and it would be useless. And so I think one of the surprises of deep learning was that, oh no, you can do millions of dimensions, and it's not convex. You will go to a false local minimum. You will never find the global minimum with probability 1, but you know what? There are lots of decent local minima, and there's just so many ways down in millions or billions of dimensions, and these little ReLUs are convex enough. It works out better than anyone really expected, I think, until Stephen Hinton wrote it down in the paper 1986, I think it was. Anyway, so that's what we're doing, is we're trying to blend this incredibly powerful nonlinear modeling that can be trained with gradient descent, very, very simple optimization strategy. We're trying to combine that with everything we know how to do before, and make that differentiable, because you put it all in Python and you can optimize everything together. And that's what DDSP started in a big way. And it's still going on. I mean, I think there was 3 papers at the last DAFX on DDSP type stuff. So you can see it, spreading and spreading. And so to me, that's anything you want to do, find a way to blend it, find out how much you need from a neural net, how much you need from normal signal processing, and you're just going to see results upon results for years to come, and it'll be fun.
Well, thank you. I think we are running out of time, so I would like to thank you very much for this fascinating review from the early 20th century to the next few decades. And let's give Julius Smith a big round of applause.
Thank you.